Thermochemistry! No more gases! Yay! Wait, no, there's probably still gases in thermochemistry. This guy's a liar. So what's the first law of thermodynamics? Alright, so basic thermochemistry. I just like this comic. This is a very chemist thing to do. You mix two substances together, it explodes. What do? Do you avoid that? No. You think about it, and then you try it again to make sure it happens again. So, the units for measuring heat. The joule is the SI, or System International system unit for measuring heat. So 1 joule is equal to a Newton meter, or 1 kilogram meter squared per second squared. This is going to sound a lot like physics because it's energy. The calorie is the heat required to raise the temperature of 1 gram of water by 1 Celsius degree. So this is the original unit of heat measurement because it was something you could physically measure and do. The joule is the derived unit, which is probably a much better unit and helps relate it to other things in the universe. But the calorie is just super practical because you can measure it based on how much the temperature changes. So 1 calorie is equal to 4.18 joules. This is the conversion for that. So energy is the capacity to do work, and it can take many forms. There's potential energy as stored energy or the energy of position. There's gravitational potential energy. Kinetic energy is the energy of motion. And then thermal energy is an outward manifestation of the movement at the atomic level. There's also chemical potential energy, which is energy stored in bonds. And then you have heat change, or delta H, which is the amount of heat energy released or absorbed during a process. This is enthalpy. So calorimetry is a technique that we use in chemistry and physics to measure the amount of heat absorbed or released during a physical or chemical change that can be measured, usually by change in temperature of a known quantity of water in a calorimeter. So you have a known amount of water, you go through some sort of chemical reaction or physical change, and you see a temperature change, and this helps you to measure what the heat and what's going on relative to the thermochemistry of that. So this is a bomb calorimeter, which we do not have, but basically it uses a sealed fixed volume container and it burns things, and it measures how much energy they burn with and measures that temperature in water. What we use mostly is something called a coffee cup thermometer because it looks like 2 coffee cups stacked together, because it is 2 coffee cups stacked together because it works. So you have a little stirrer, and you have your thermometer and a styrofoam cover and the styrofoam cups, and you measure that change in that reaction. So exothermic processes are processes in which energy is released as it proceeds and surroundings become warmer. So this is a graph of an exothermic process. You start with energy of reactants being high. It goes over some activation energy, which is always higher than the starting energy. And then you drop to the final energy of the products, which means the difference between the starting and final position is how much heat is released. So reactants produce products plus energy. There are also endothermic processes which require heat and absorb heat, and the surroundings become colder. So the energy of the reaction starts low, you go over some activation energy, and you end up with the energy of the product. So delta H is positive. You have to put energy into this, so reactants plus energy becomes products. So define endothermic. Define exothermic. Define calorimetry. Define what a calorie is. Define kinetic energy. Define potential energy. Define thermal energy. Define enthalpy. So here's a phase change diagram. A phase change diagram shows you relative to temperatures and pressures when things melt or freeze or vaporize, what the triple point is, what sublimation is, and how these change. So processes occur by the addition of energy. So as you move this way on the graph, they're showing you that temperature, right, you're adding energy in, the temperature goes up. So processes occur by removal of energy going the other way. So there's lots of ways that phase change diagrams can look, but they represent phases as a function of temperature and pressure. The critical temperature is the temperature above which the vapor cannot be liquefied. The critical pressure is the pressure required to liquefy at the critical temperature. And the critical point is the critical temperature and pressure. So for water, the critical point is 374 Celsius and 218 atmospheres. So water phase changes, this is a different sort of a phase change diagram, but it shows you that as you add energy, the temperature doesn't change when it's changing phase. So you add energy, the temperature goes up for ice, and then as you add more energy, it transitions from ice to water and the temperature stays the same. So temperature remains constant during a phase change. Then you heat up the water, and then as water becomes steam, you don't change temperatures. This is why we have a boiling point of water and a freezing point of water. It's a fixed temperature. So this is another way that a phase diagram can look. It looks much more complicated and much fancier, but it's still basically giving you the same information. So critical temperature is the temperature above which the vapor cannot be liquefied. Again, there's your critical point. The critical pressure is the pressure required to liquefy at the critical point. And the critical temperature and pressure for water, again, 374 and 218 atmospheres. So phase changes, they show you by name. Here is a one for water. You'll notice that the line leans backwards for water. This is because as you increase pressure, it actually wants to become liquid more because solid has more volume in water. For something like carbon dioxide, that line leans forward, the solid-liquid transition. You also get, for carbon, it's even more complicated because there's multiple solid phases. Sulfur has rhombic and monoclinic solid phases. It has a liquid phase. It has its vapor phase.